projectile motion here. I'm going to type it up here. Whoa. All right, so if you watch that little Dan Meyer video there, he tossed that basketball into the air. You guys did a great job of drawing some pictures to go along, or some lines that match it. So I'm going to try to recreate a little strobe kind of a picture here where my object is getting closer and closer together. My times, I'm trying to make them close to being equal. So this is an object as it goes up, 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 and then down, 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 down. So that's like the full projection there. The fancy name for the path of a projectile is called a trajectory. So it's just a word that means path of a projectile. Now, there's no vocabulary on your tests or the AP exam or anything like that, but when you're reading a question and it says, it gives you some information about the trajectory and it uses that word, I want you to understand that it just means the path of the projectile. Okay? All right, so when we toss something into the air, we give it an initial velocity. Now, it had to be forced by your hands, and you've already studied forces and how we have an unbalanced force acting on an object. So the basketball did get a push from Dan Meyer, but as soon as it left his hands, it was no longer being pushed by him, and it was moving through the air in true projectile motion, where the only thing acting on it would be what? The acceleration due to gravity. Now, your answer as gravity is not really complete enough. Gravity is a phenomenon that causes a force, that causes an object to accelerate. So by saying gravity, you're not really being specific enough. Okay, you need to tell me what the gravity was doing, if it was applying the acceleration, if you're looking at the acceleration due to gravity, or the force due to gravity. Okay, but if you just write gravity, you're not going to get full credit, unfortunately. Okay. Okay, so when it takes off, it's moving in two directions. It's moving in the x direction. I'm going to draw a dashy dash dash component there. Dashy dash means it's not the vector, it's just a piece of the vector. And I'm going to label it the initial velocity in the x direction. And then, how about a dashy dash 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 for the y direction? That would be like the initial velocity in the y direction. So if no acceleration, that means that my velocity at every time is going to be exactly the same in the x direction. So pretend like I'm really awesome and I can draw all of these little red dashy dash arrows as exactly the same length. So the acceleration in the x direction, I'm going to start making a few notes down here. So for my x direction, the acceleration in the x direction is 0. Okay? Now, what's happening to the velocity in the y direction? Look at your y position time graph that you sketched out. Was it increasing, decreasing? It was decreasing, that's right. So if I show a decreasing vector, maybe I won't make it quite as long, but still up and even shorter. And then what happens to the velocity in the y direction at the very highest point? It becomes 0 in the y direction only. Is it still moving in the x direction at the highest point? It sure is. Otherwise it would fall straight down. But it's going to continue to go over here. So it's always moving in the x direction at the same speed. Oh, our velocity in the y direction is decreasing, and then it gets to 0, but the acceleration due to gravity is still acting on it, or gravity is still acting on it, causing it to accelerate. So what happens to our object after it passes the highest point? It starts coming back down. So what would the velocity vector look like at this point right here? Same, if I was an awesome artist and this was exactly the same height, wouldn't this one be like that? Same magnitude, opposite direction? All right, what about here at the next step? Maybe like that? Does that look okay? And then in my very last step, maybe something like that. I think I drew it a little bit too long. So this is my final velocity in the y direction. What's it equal to? Now, I'm not talking about once it hits the ground. I'm talking about the moment right before it makes contact. It's definitely in the negative direction. And in terms of my initial velocity, look at this. It's going to be the same but negative. That's right. It'll be equal to negative v naught y. That's if it goes from height 0 back to height 0. Okay? Yeah, what's up? So in the y direction, what is the acceleration? Or what's causing the acceleration? There's the acceleration due to gravity, which for our problems is approximately 10 meters per second squared. Again, I'm not going to let you do or use anything that would be inappropriate on the AP exam, so please use 10. Because you can use it on the AP exam. You can use it on all my tests. It makes things so much easier. Add, subtract, multiply, and divide by 10. Right? So much faster, especially when you don't have a calculator for a multiple choice section, because that's what reality is going to be like in May. Right? Okay. All right, so now let's look at this initial velocity in the x direction. It looks like the base or the adjacent side to this angle right here, and this is your initial velocity. So how could we find the value for the initial velocity in the x direction? Think back to those vectors and forces and stuff like that. The hypotenuse times cosine theta, and our hypotenuse in this case is not a force, it's a velocity. So our initial velocity in the y direction would be v naught sine theta. Now, when you toss something in the air, and it's moving in the x direction and the y direction at the same time. So, does it move in the x direction from the time it left my hand till right before it hit the floor? Was it moving in the x direction for a longer amount of time than the y direction? Or was it moving in the y direction for more time? Or were they the same? Same. It's moving in the x and y direction at the same time. So time is the only quantity that actually links the x and y directions together. So your time for the x direction, your time for the y direction will be the same. Now, once upon a time, long, long ago, you derived using a graph 3 kinematics equations, and I'm going to remind you of them. We have what? V naught equals V. Oh man, I was doing so good and then I just bummed out. V equals V naught plus AT. And then delta X equals V naught T plus 1/2 AT squared. And V squared equals V naught squared plus 2A delta X. And do not be fooled, you must know these. It's essential for your success. Okay? Now, those are motion equations. Remember, this was from the line on the velocity time graph. This was for the area under the velocity time graph. And the third one was derived by eliminating time from the first two. So they don't fall out of the sky and land on your paper. They come from something, okay? We can derive them. I don't want you to ever feel like you just have this formula to use. Okay, so now let's look at the x and y direction for the motion equations in the x and y direction individually. So if my acceleration is 0, what's going to happen to this first equation? If this was Vx equals V naught x plus 0t. Oh my goodness, it tells me that the initial velocity in the x direction is equal to the final velocity in the x direction. Isn't that what our little picture up here shows me anyway? Isn't this our final velocity in the x direction? It's the same throughout. Does not change for true projectile motion. Remember, we sucked all the air out of the room. We're in a magic physics room, so we don't have any drag forces, friction, air resistance, anything like that. All right, let's look at the second one here. So when I write the delta x equation for just the x direction all by itself, whoops, too far, I'll get a delta x equals v naught xt plus 1/2 at squared, which is 0, so just stop there. Okay? Now look at that third one. V squared equals v naught squared plus 2a delta x. So v x squared equals v naught x squared plus 0. What does that tell you again? That the initial velocity in the x direction is equal to the final velocity in the x direction. So it looks like we only have one valid equation to use for the x direction to get you anywhere. All right, so now let's look at the y direction. Do we have an acceleration in the y direction? Yes, acceleration due to gravity. So we've got Vy equals V naught y. Tell me about the slope on your velocity time graph that you created from the basketball picture. It was a negative slope on the velocity time graph. Okay, so that means this would be negative GT. Right? And in our, instead of X, I'm going to use Y. How about that? We're just dressing up for Halloween in our Y costume. So delta Y equals V naught YT minus, because it would be a down facing, a concave down parabola, 1/2 GT squared. So just like free fall motion equations, right? So Vy squared is equal to V naught Y squared minus 2G delta Y.